Hey everyone, welcome. Today we're going to tackle something that sounds super complicated but is literally happening all around us, every single second. We're talking about randomness, but randomness over time. We're going to see how we can actually find patterns and even make predictions in systems that seem completely chaotic. Ready? Let's dive in. Okay, so think about it like this. A single dice roll. We all get that. It's random. It's one single snapshot in time. But what about the stock market over a whole year? Or, the number of people in line for coffee, which is always changing. Or the signal strength on your phone going up and down. These things aren't just a one-off event. They are constantly changing, randomly over time. So, how in the world do we even start to describe that? And this is the core idea for today. It's such a great way to think about it. A single random event, like one coin flip, is what we call a random variable. Think of it as a snapshot, a single photo. But when you have a whole sequence of these random events happening over time, you get what's called a stochastic process. It's not just a snapshot anymore, it's a movie. It's the whole story of how something random evolves. Right, so let's get a little more formal with this whole movie randomness idea. We need to learn the language that lets us talk about these moving, uncertain systems in a way that makes sense.
Now, don't let the mathy look of this scare you off. I promise, it's simple. All this definition is really saying is that a stochastic process is just a collection of random variables. You've got one for each point in time. So if x of t is the price of a stock, then x at 9 a.m. is one random variable. X at 10 a.m. is another. And the whole collection for the day is the stochastic process. It's just the official way we film our movie.
And this isn't some abstract theory. This stuff is everywhere. The number of people waiting in line at the bank, the static-like fluctuations in an electronic circuit, the daily up and down of a stock price, the flood of calls at a call center, or even just the signal bars on your phone. All of these are real-world stochastic processes. They're movies of randomness playing out all around us. Okay, so if stochastic processes are movies, then Markov chains are like movies with a really, really simple plot rule. They're a special kind of stochastic process, and this special rule actually makes modeling the world a whole lot easier. Let's see how that works. So, picture this. You've got three friends, let's call them A, B, and C, and they're just tossing a ball around. The rules are super simple. If A has the ball, he always throws it to B. No exceptions. If B has it, he always throws it to C. But C is a little unpredictable. If C gets the ball, there's a 50-50 chance he'll throw it to A or to B. This simple little game, that's a perfect example of a Markov chain.
So what's the big deal about this game? Well, it follows a crucial rule called the Markov property. And here's what it means. Where the ball goes next depends only on who has the ball right now. That's it. It doesn't matter how it got to that person. The path could have been ABC or ABC, ABC. None of that history matters. The only thing that predicts the future is the present moment. The system is completely memoryless. This memoryless idea is key. A really great analogy is a simple board game, like snakes and ladders. Your next move is all about the square you're on right now and what you roll on the dice. It makes zero difference whether you got to that square by climbing a giant ladder or by just slogging through one space at a time. The past is totally irrelevant. You know how movies have different genres, like comedy or action? Well, Markov chains can also be sorted into different types based on how they behave. And if we can classify them, it helps us predict what might happen in the long run. Let's check out a couple of important types. So, two major types are regular and absorbing chains. In a regular chain, you can eventually get from any state to any other state. Our ball game is a good example. The ball can always eventually get to any of the three boys. But an absorbing chain is different. It has at least one state that's like a trap. Once you go in, you can never get out. Think of landing on the finish square in a board game. Game over. You're absorbed. So we know these systems are random and always changing, but what if, underneath all that chaos, there's actually some kind of stability, a predictable personality? This brings us to a really cool idea called stationarity. A process is called stationary if its basic stats, like its average value and how much it tends to vary, don't change over time. Even though the individual results are random from moment to moment, its overall behavior is stable. And that's a huge deal. Because if a process is stationary, we can pretty much assume its future is going to behave, statistically speaking, just like its past. So what does this actually look like? Well, a stationary process is kind of like the steady hum from a fan. The actual sound waves are random, but its average volume, its overall character, stays the same. A non-stationary process, on the other hand, is more like a song. It has quiet parts and loud parts, right? Its stats are always changing. A great example is counting the calls at a call center. The total number of calls can only go up during the day. Its average is constantly changing. So boom, that's non-stationary. Okay, so we've talked about movies of randomness, memoryless ball games, and the steady hum of a fan. But why does any of this actually matter? Well, it turns out that understanding these concepts lets us model, predict, and even improve an incredible number of things in the real world. And the applications are seriously huge. Queuing theory uses this stuff to predict wait times for everything from the line at your bank to highway traffic. In finance, this is the backbone of modeling stock prices and figuring out investment risk. Engineers use it to predict how long a machine will last before it breaks down. And our entire phone and internet system relies on it to manage network traffic so things don't get overloaded. It's literally everywhere.
So there you have it. We've seen that even in systems that seem totally random and chaotic, there are hidden structures, these underlying rules that we can understand and actually use. We've gone from a simple snapshot of a coin flip all the way to watching the movie of the stock market. You kind of have the tools now to see the world in a new way. So I guess the only question left is, what real-world movie of randomness are you going to analyze first?